Hi everyone, my name is Moshe Shienman, and this is the slices perspective for incremental nonparametric inference in high-dimensional state spaces, which is a joint work with Levy-Or, Professor Michael Kaess, and Professor Vadim Indelman. Modern mobile robots and autonomous systems are expected to reliably and efficiently perform various tasks such as localization, mapping, and object manipulation. In real-world scenarios, these agents must operate under different sources of uncertainty, such as noisy measurements, imprecise actions, and dynamic environments in which some events are unpredictable. When uncertainty plays a significant role and probabilistic reasoning is essential for making safe and informed decisions, access to the full posterior distribution, representing the agent and the environment, is crucial. Therefore, probabilistic inference algorithms providing posterior distribution estimates are commonly used to address these challenges. However, there are still many challenges in real-world scenarios. First, handling high-dimensional state spaces and operating in real time is far from trivial. Moreover, in real-world problems, posterior distributions are often non-Gaussian, and obtaining closed-form analytical solutions is very challenging and frequently impractical. Modern probabilistic inference algorithms leverage different probabilistic graphical models such as factor graphs and Bayes trees to solve or approximate such problems. A factor graph is a bipartite graph with two types of nodes, factor nodes and variable nodes. The variable nodes represent the random variables in the estimation problem, whereas the factor nodes represent probabilistic information on those variables. The graph edges, linking factor nodes to variable nodes, encode connectivity based on these variables associated with each factor. In this small example, we first see an agent in an initial position represented by the random variable x0 and some higher probabilistic information represented by the factor f0. As the agent moves to a new position, a new variable node x1 and a new factor node f01 are added to the graph. The probabilistic information encoded in f01, representing the transition function, is usually assumed to be modeled with known noise distributions. At this pose, the agent also requires an observation to a specific landmark within the environment, and a new variable node L1, as well as a new factor node F1L1 are also added to the graph. As the agent takes another step, it requires a second observation to the same landmark, and the corresponding variable and factor nodes are added. At any given time step, the given factor graph represents a factorization of the posterior distribution in terms of process and measurement models given by the product of all factors. To perform inference and retrieve joint and marginal posterior distributions, different variants of the forward-backward algorithm are commonly used. This algorithm operates in two passes given a specific variable ordering. During the forward pass, a single variable is eliminated from the factor graph in each step, following the elimination order. In this example, x0 is first eliminated from the graph. The eliminated variable node, as well as all the factor nodes connected to that node, are first removed from the graph. The joint density, defined by the product of all removed factors, defines a conditional, represented in blue, which is added to a base net, and a new factor, f1u, represented in red, which is added back into the reduced factor graph. Note that after each such intermediate step, we have both an incomplete base net and a reduced factor graph, which defines the density on the remaining variables. Once all variables are eliminated, the forward pass is completed, and the joint distribution can then be expressed as the product of conditionals produced in each step. This product now defines base net. To recover marginal and joint posterior distributions, a second backward pass is performed. Starting from the last eliminated variable and following the elimination order in reverse, these distributions are calculated using back substitution. However, while there is a closed-form solution in the Gaussian case, in the general nonparametric case, it often does not exist. As such, all partial posteriors, conditional, and marginal distributions throughout both the forward and backward passes must somehow be approximated or reconstructed. Several state-of-the-art methods address this issue in a non-parametric high-dimensional setting. Fourier et al. Suggested to approximate non-Gaussian posterior distributions through the use of samples and kernel density estimators. Specifically, in each step, the approximation process employs an iterative nested Gibbs sampling approach to generate samples from partial posteriors, which are then used to construct new approximations of posterior distributions using kernel density estimators. Huang et al. Exploited the expressive power of neural networks and trained normalizing flows to model conditionals that factorize non-Gaussian posterior distributions during a forward pass. Once all conditional samplers are learned, samples are drawn from the posterior distributions in a backward pass. Our key observation is that these distributions can be directly reconstructed without the need for any additional learning techniques or kernel density estimators. In fact, a joint probability function for several random variables can be seen as a high-dimensional surface from which conditionals and marginal distributions can be calculated. We present this concept using a low-dimensional example. Consider the joint distribution over two random variables x and y. Assuming our goal is to recover the marginal distribution over x, we simply need to integrate out the random variable y. As y is a continuous random variable, and there is no closed-form solution in the general case, we need to approximate the marginal using n samples of y. For each such sample, the conditional p x given y is given by a specific slice from the true surface representing the joint distributions. Once we have n such samples, we can simply sum or stack them and normalize to get the approximated marginal distribution, which in this case is represented by the blue line. And so our first contribution in this work is to follow the forward-backward algorithm and leverage slices from high-dimensional surfaces to approximate joint and marginal posterior distributions without any further intermediate reconstruction. Our hypothesis is that by avoiding any additional intermediate approximations and accessing slices directly would produce better estimates. Looking at this toy example with 3 variables and 3 factor nodes, when eliminating x0, factor f1u is now approximated using a mixture of slices taken from the high-dimensional joint surface induced by the factor f01 at sample points of x0. This procedure repeats until all variables are eliminated. Once the forward pass concludes, a similar slices approach can be used in the backward pass to approximate the marginal distributions for all variables and the joint distribution. Our second contribution addresses incremental inference. In a real-world application, a real-time online solution requires continuous updates and providing estimates whenever new measurements are added. We continue with the same toy example, where after taking 2 steps and doing inference, the agent now takes a 3rd step and observes a new landmark L1. Incremental inference was initially developed for the Gaussian case. The underlying observation in these approaches is that addition of new measurements affect only specific parts of the original factor graph. As a result, there is no need to redo the entire forward-backward inference process. Instead, an incremental forward pass is conducted, focusing computation solely on the affected variables. This process is called re-elimination, and it significantly reduced computational costs by reusing previously computed information and selectively updating relative section of the factor graphs. Moreover, performing full back substitution in every iteration can be computationally expensive, particularly in large-scale problems with complex factor graphs. As a result, an early stopping heuristic in the backward pass was first introduced in ISOM 2 to significantly reduce computational cost in the nonlinear Gaussian case. In our work, we extend this notion and introduce a novel early stopping heuristic for the nonparametric case. We propose leveraging the maximum mean discrepancy metric as a heuristic for early stopping. This metric is suitable as it is used to assess the dissimilarity between 2 probability distributions relying on samples. During the backward pass of each incremental step, we calculate and cache the most recent marginal distributions. Given a new marginal and a previously found marginal for a given variable, we use the MMD metric to evaluate the distance between the 2 distributions. If this distance is below a user-defined threshold, we stop the backward pass. We tested our approach using several synthetic and real-world datasets. In this experiment, we used the Plaza dataset, which contains a sequence of odometry and range measurements to 4 unknown landmarks, gathered by a vehicle navigating a planar environment. This range measurement SLAM problem is challenging because it involves both nonlinear measurements and non-Gaussian likelihood models. A single range measurement from x0 to some landmark L1 can only locate the landmark on a 2D sphere. This true landmark location can only be resolved for more measurements as the robot traverses. In this experiment, we perform incremental inference and evaluate at each time step both the runtime and the root mean squared error, which measure the discrepancies between the ground truth and samples from posterior distribution. We compare our method against the two presented state-of-the-art methods and show that our slices approach achieves superior accuracy and significantly enhances computational efficiency, reducing time complexity by an order of magnitude. To conclude, this work presents a slices approach for incremental nonparametric inference in high-dimensional state spaces. We introduced a novel early stopping heuristic criteria to further speed up calculations. And in the paper, we show how this approach requires less sample and consistently outperforms state-of-the-art nonparametric inference algorithms in terms of accuracy and computational complexity. Thank you for listening, and I highly encourage you to read the paper for further analysis and results.